nataka kusikia nani but I'm sure when I will be talking of how do we call it, a chi-square test or a t-test, at least you will be able to understand what I will be talking about. On what we were supposed to cover yesterday, I have updated some commands there and inserted onto this R script file. And this topic here, or this project, is a sample project that one of you can do in his or a final or in a 4th year, as a 4th year in the project. So uanga tunafanya project, so you can choose to do either, for example, I choose the time series analysis. Kuna mwingine anaweza kuja fanya the multivariate. I'm talking as in the field of statistics, that is applied. So you can choose any topic that you want to do a project on. You can choose either the diagrams, string diagram. You can choose a project on a parametric test, the fundamentals of computing, for example. You can choose regression analysis. You can choose multivariate time series, but now for this one I chose time series, but I mentioned on a model called the ARIMA model, What is a time series data? What is a time series data? Nataka tuongee. We are finalizing everything today. What is a time series data? I want to hear from you. King Muller.
I think it's data that depends with the time. It's recorded in different times.
Yeah.
Intervals of.
Very good. Very, very good. And with this data, you can use statistical techniques either to predict the outcome, of the future outcome of that data, or rather you study the pattern and you can predict how future will be. And I recorded some data here. This project was for an hospital called Jumuiya Friends Hospital. How many of you, okay, mnaweza kuwa hamjatoka hiyo side. An hospital in Vihiga County, it's located in a Misi constituency. So what happened, nataka mpate content vizuri. This hospital, the management of the hospital was unable to allocate nurses, or rather the human resources, to serve or to offer their services during a month. So unapata in some time the number of patients zinakuwa increased until the number of nurses or the human resources in that particular hospital was overwhelmed. So now the management of the hospital suggested to do a research of or to come up with a project or a way of estimating the number of patients that will be attending that specific hospital during a month. So after that you can be able to determine the number of workers you will allocate in that particular month. So I was called by there's somebody called Dr. Alila. Dr. Alila is the COD, the School of Mathematics in Masinda Malero. So I was involved in that project, and we used this data. So the data here was specifically from inpatient, not inpatient, the outpatient. The data was from the outpatient records, and it was recorded on monthly basis. And we decided to pick data from 2018 up to 2020, so that we can predict now from 2022 going 2023, 2024, that way. So and remember I told you that we cannot do, or we cannot learn this language to maliza even with a year. For example, here you will notice that we have 3 packages. We have a package called forecast, we have a package called T-series, we have a package called ggplot2. I'm sure we have already covered some bit of ggplot2, but we haven't covered the forecast or the T-series package. So in these packages, the functions that I will be using here will be from those packages. So we have the TS. We have the TS function. TS function in time series is used to configure or to tell the compiler that the data is assigned, or to direct the compiler to assign data in time series format. So in time series. So let's execute these 2, or let's call these 3 packages. This is forecast. So you run this first. You run the T-series package and the library ggplot2 package. So from there we have a vector. We have a vector called data1, and data1 has these figures here. Mnaona venye ni mingi. So this data was recorded on monthly basis. So we can run this command here and call the data1. So these are the content of data1. These are the content, or the values that are in vector called data1. Check the syntax for the TS function. TS function follows this syntax. You have to specify the data first, and the starting point, then you give out the frequency. I remember yesterday we said that TS data, or rather we said that the frequency in TS function is used to return the intervals under which you want your data to be assigned to. For example, we send a frequency of 12. A frequency of 12 is, when you walikuwa jana, what? Frequency of 12 means what? Frequency of 12, Mr. John, Malvin. frequency of 12 means what? Nani anakumbuka tukisema a frequency of 12 means 12 equal 12 equal what? Equal months. So in frequency here, the TS data takes frequency as 1 here. So. But when you equate this here to 12, you are telling the compiler to divide that here in 12 equal parts. In 12 equal parts.
Sorry, excuse me.
Yes.
When I execute the library forecast T series, I'm getting the message that there is no package called forecast.
Okay. What does that message means? It means you have not. Okay, very good. Just do it.
Which package? Well, I install a package called forecast.
Yes, and another called T series. So I expect ukipata such an error message, unajua tu what to do, si ndio?
Okay.
Yeah. Okay. Yeah. Nani mwingine anapata the same? I decided not to input the commands for installing them here, so that ukipata that message error, you know that message, that package is not in your machine. So from there you can install. So install forecast package together with the T series package. Okay, acha nione wenye waja install. Rama, the 22, have you installed the package, the forecast and the T series before we proceed?
Yes, they are installing.
Okay. Mr. Mbodo, John?
Mine failed. I'm thinking of updating my software again and see if they will install.
Okay, sawa. Nani mwingine aje install? Mary Ndama. Mary.
Yes.
Have you installed the forecast and T series?
Not yet.
Just install as we go on, sindio?
Okay.
Now, the TS function now, and the TS function, you have to specify the starting point of your data, or rather the month or the starting point where your data was, where your first data was recorded, or rather the oldest data. So or the first data that you want to analyze, you have to specify the starting point. So my data here, data 1, is starting from January 2018. So I will give you a task here. You search on how to insert data on monthly basis. For example, you want to start from 2018 February. How do you insert that data here? So that is your question. So from there, when we execute this command, our data here is cont k. Our data is cont k, the TS data set. The TS data, the data in time series format is cont k. So I have assigned every operation here to letter k, or rather a variable k, and I can execute the k and see now my data is not in vector form. We don't have data 1 in vector form, but we have converted data 1 from vector to time series, from vector to time series format. So you can see here we have 2018 from January up to 2022 November, up to 2022 November. So this is the last data in our data 1 records. 418, you can see it. Then we have 621 as our starting point. You can decide to have a view on the plot of k. Let's see. Okay, when we plot k, you can see that our data is k here. This is the starting point from 2018 January. You can see how the attendance was behaving. So tunaona at 2018 at around June, July hapo unaona the number was very low. Then after that the should end up. So this is the behavior of attendance. This is the behavior of the attendance. But now in time series analysis, there are some, how do we call them? There are some assumptions that must be met. There are some assumptions that must be met. What do you understand by the name stationarity? Stationarity. What do you understand by the name stationarity? Okay. By stationarity, it means that this assumption or this condition of stationarity of data will help us, or will help the programmer not to have predictions that are out of the bounds of your data. So for example, I don't expect to predict my data from this point here. So from 800 I say we are going to 900. In this month alone, where we have this sharp projection here, it means in that particular area maybe there was an accident in that particular from, let's say, from morning. It might be even a bus accident. So we expect very large number to be recorded on that particular day. So we don't predict our data, or other time series data, based on some outcomes like those ones. You have to test your data to be on the same bound, That is what we mean by stationary. by stationarity. So if you have any question, you can ask. You can ask. Now we perform a test that is called the ADF, or the augmented Kifula test. This test is used to test for stationarity. This test is used to test or to check whether there is stationarity in your time series data. So are we together? Are we together to that point? Nani hajaelewa? Mpaka hapo, who has not understand what you are doing? Who is not understanding? Mr. Malvin.
Yes.
Unapata what is an ADF test?
Yeah. Ni tu ggplot tu na ilikata kurun.
Sababu uja call the ggplot 2 haiko kwa mashini yako?
Iko hadi ukicheck iko, but when I run it failed. It can't plot any graph. Well, the other packages zinawak
tu, si ndio?
So maybe is it setting or what? Maybe you can check your settings then share. Maybe later, not now.
Okay, sawa. So I will check and
also the version that you're using, Mwalimu.
Pardon?
Maybe you can share with us the version of R studio that you are using.
I'm using a version. Okay. Just type the name version in your console and run the command part and run. So I'm using R version 4.2.3. It was released last week.
Okay.
Yeah, even me, I have the same, but it can't run ggplot2.
ggplot2. Have you installed the ggplot2 package?
Yeah. To an extent, they sent a text that it's in my local DC.
Able one of you to share the screen with us to know what's the problem. Sawa. I'm waiting for one of you to share the screen with us. Malvin. Hey, Mr.
Let's Jono Puresha is. I can't share.
Pardon? Should we continue or I just wait one of you to share?
Just continue. All to share his. I'm using a phone.
Oh, so
while doing it practically through my PC.
Oh, I understand. So now we have the ADF test, or the augmented Kifula test. When we run this command, what do you get? You get this is an augmented Kifula test, and we have data K. This is a Kifula test. So this is the test, and the compiler has taken or has executed this test based on the 3, on lag on the 3. So from for example, lag on the 3 means from our data, check here, from our data it means this is lag 1, 621 is lag 1, 452 is lag 2, 453, 456, 57 is lag 3. So now the operation that is done here is combined with the other one from here to that point until the data is stationary. Unapata, until the data is stationary. But now, what do you conclude, or what do you consider to conclude that your data is either stationary or not? Is either stationary or not? In any test, today we are purely in statistics. In any test that you do or that you perform, you must have the hypothesis. You must have the null and the alternative hypothesis. For example, I'm using a PC. I'm using PC to read this data, but if we are calculating manually, like the ones that, like how university students do in exams, you will get this as your test statistic, or the Ndikifula statistic. You will get this point. From this point now, you compare with what? You compare with the Ndikifula test in your tables. Sindio? In your tables. Kuna hizo tables zinatumika in campus. So you compare this point with the one in your table. But now, because I'm using computer, I will not use this part here to do my conclusion on whether to reject or fail to reject null hypothesis. I use what? I use the p-value. Now, first of all, you have to ask yourself, before you perform a test, what are the null and alternative hypothesis in ADF test? So are we together? So the null hypothesis of this ADF test is that the time series contains a unit root, or is non-stationary, So the alternative hypothesis is stationary. The alternative hypothesis is stationary. So I want to hear from you. I request to hear from you. How do you use p-value to reject or fail to reject the null hypothesis? Because what you are testing is the null, not the alternative. Sindio? How many of you are doing statistics? Here. Where is Mr. Kabila? Where is Mr. Kabila? Okay, let's continue. Now, what we use in statistics or in computers to reject or fail to reject the null hypothesis is the p-value. And in default, the alpha, computer will be using an alpha of 0.05. That is 95% confidence interval. So confidence level. So that is the default alpha that is used in statistics. And what you do, you compare this part, you compare the p-value with 0.95 or rather 0. You can compare either way, from left with the 0.95 or from 0.05. 0.05. So from this part here, we have 0.02. We have 0.02. Is 0.02 greater than the significance point of 0.95? Or rather 0.05? We say no. This point is not greater than 0.05. So what do? We reject the null hypothesis. We reject the null hypothesis if p-value is less than alpha. So we reject if p-value is less than alpha, and fail to reject if p-value is greater than alpha, and our alpha is 0.05. That is by default computer calculates this test using alpha of 0.05. So this point is less than 0.05. So we reject the null hypothesis and conclude that our data is stationary. Our data is stationary. Are we together up to that point? Okay. That is the augmented Decay-Fuller test. So we are now progressing with our project. So that is the output. That is the output. Now, in time series, we have a model. We have a model that is called ARIMA. That is called ARIMA. And ARIMA model. Okay, who has heard of something called ARIMA model in modeling, in statistical modeling? Who has heard of ARIMA model? I want to hear from you. Nani amewahi sikia jina ARIMA? Nani amewahi sikia ARIMA? In statistical.
I have.
Yes.
Yes, I know.
Okay. ARIMA is made up of the autoregressive pattern, the moving average, sindio? And the integrated part. So this model called ARIMA is actually used to predict. So for example, I can tell you to predict the sales of 5 days from now using 2 days moving average. So you multiply, you add today and tomorrow values from today and tomorrow, then you divide by 2 tomorrow, and the day after tomorrow you divide by 2. So yeah, so you can predict the other part. So that you can predict the other part. And for you to get the values of the autoregressive part, we can use the ACF and PACF, or rather the moving average ACF, and PACF of K will give us the other part that is forming that particular model. For example, when we execute the ACF of K, let's see, when we execute the ACF of K, ACF means, what is ACF? What is ACF?
Autocorrelation function.
Yeah, very good, very good. The autocorrelation function. So the autocorrelation function, it can be used now to give us the which part of the model. Which part? Is it the AR or the other part? We have the AR or the MA. Which one? Okay. By looking at the autocorrelation function, that is the ACF, and the partial ACF plot of the different series, you can tentatively identify the number of AR and MA. And MA, that is the moving average in terms that is needed. So you are already now familiar with the ACF. So with the ACF plot and the PSEF plot. But now you may predict or you may come up with those points that are going to form our model wrongly if you pick, for example, we want to pick how many excuse me, we want to pick these lines that are outside our bounds. They can be used to form our part of AR, and the other for PSEF from the part of the moving average. So for example, if we use this one here, we have 2, so we have 2 for ACF, and for PSEF, that is the partial. What do we have? Yes, for the partial we have 1 here that is outside these bounds, and we have another one here that is touching those bounds, but it's not breaking that dotted line. So if you choose from the previous one, which had 2 and this one has 1, you may get confused which point is true, which point is true. So which point is true? From there now we apply a function from the forecast that is called the auto-arima function. We apply the auto-arima function. Auto-arima function, this function will give us the specific point of the autoregressive part, the integrated part, and the moving average part. So if you check in here, we have 3 criteria for modeling. So we have theories that are used for modeling, and they should not conflict each other. So one model should not give different outcome from the other theory, or theories should not contradict. And the first theory here that we are going to apply is the AIC. This is K model 1, or rather the K model. I have K model of auto-arima of our data K. Remember, our data K is in time series. IC, this is the information criteria that you want to select your model from this data. So we want to use the AIC. AIC means the archaic information criteria of selecting model. Tukiingia kwa the archaic information criteria of selecting model, hapa kuna theory mingi sana for those who have done statistics, ama unaweza enda ufanya online research. Utaona methods zenye the methods or the theories that a scientist by the name archaic introduced for selecting a model of the ARIMA. And when you execute this command here, what you will get is a model, and R will produce all the possible models from that part. So all the possible models from that information, and choose the best model, from these models. For example, check here the archaic information criteria with the help of auto-arima function is selecting a model with the autoregressive 1, integrated part 0, and the moving average of 0. So Ukikuja kuangalia that model in this part here, let's compare this model here with the inferences from this part. 100 iko wapi? Let's see. Where is the model? I think it's here, isn't. Yes, this one here with non-zero mean. It has a value of 734. 734, yes. 734 is the minimum inference from this part. So the autorima function, with the help of theories that are related to the archaic, this is the best model to use. And we will use the same model. We'll use the same model with other theories. Let's see. Let's prove the other theories. This is the other theory. The BIC. BIC means what? I want to hear from you. BIC means what?
Bayesian information criteria.
Very good. The Bayesian information criteria. So, what of the AICC? AICC? I want to hear from you.
It is a corrected archaic information criteria.
Very good. The corrected archaic information criteria. Sawa. So, even if you execute this command under the Bayesian inference, we are getting the same model, with our data. We are getting the same model, and if you check from this point here, you will get the inference statistic is very small. Let's see. Within a zero mean of 100, within a zero mean we have 741. All these values of inferences here, they are greater than 741. So this is the best model to use. That is the best model to use. What of this other part here? Let's see. Yes, even that one, we are getting the same model of ARIMA function, of ARIMA of under 1, 0 and 0, of under 1, 0 and 0. You can call the model now to get the summary statistics of that model, of the K model. Let's see, let's learn what is contained in this part. Now, this is ARIMA of under 100. This is autoregressive part of 1 integrated 0, and the moving average of 0. We have the coefficient. We have the coefficient of the AR, the autoregressive part, and the mean. Then from there we have the standard errors of the AR. Of the autoregressive part we have this one, and of the mean we have this one. What are importance of these ones here? What is the use of sigma, and what is the use of what does this mean? The log likelihood and sigma. I want to hear from you. What does log likelihood mean? You have seen the AIC, nimeonyesha pale inatoka, the AICC and the BIC, the Bayesian. Okay, this point umeona pale zimetoka, but what are the use of these ones here? Acha tuende tukiinterpret the final model, mtaona how log likelihood is important, is of importance, and the sigma, sawa. From there now, for you to have for you to have a model that will give you accurate estimate, you have to test for residuals. Sindio? You have to test for residuals. So remember, in estimating, residuals of time series should be normally distributed. Sindio? Should be normally distributed. But for you as a data analyst, how do you say or how do you tell that this data is normally distributed? Which characteristics will you use to conclude that indeed the residuals of your model is normally distributed? Because residuals is what is tested under these parts. Okay, how can you tell that the residuals are normally distributed? Where is Mr. John? Kuna mwenye aliniambia anafanya statistics. How do you tell that data is normally distributed? I want to hear from you. Clear Wairimo. How do you tell if data is normally distributed? Under normal distribution curve, the curve of normally distributed data is symmetrical, or it takes bell-shaped curve. So and let's have a view on it. We can have a view of what is L. So these are the residuals after. And how do we obtain the residuals? Residuals are obtained after you plot, or after the actual points that are used to plot a graph, then you subtract with the means. So what is remained after you plot, or after your point of being used to plot a specific model? Then we can histogram east. Remember, east here is under Q ggplot2. ggplot2 east K model and residual. Let's see. Okay, if you check keenly here, our histogram has a bell-shaped. Check here, we are from 0 up to negative 300. We are from 0 up to 400. And this is the point here. This is the longest bar. And if you do like this, you can indeed see that the shape of this
maybe you can just include that density curve on that histogram, so that you can visualize properly the distribution of residuals.
This was for the bars. Sikuwa nimeandika hiyo function hapa, but kama nimekupea isi, you can plot this part here for the curve, sindio? Sijui ni kwa nini nilisahau kuiweka. So unaweza weka ukiwa mwanafunzi, sindio? Yeah. so you can put, sababu naona hatujafika hata nusu ya hii, so just take your time uone, just do research. Hizi vitu ziko online everywhere. Search how to insert and then set a plot curve on an histogram, utapata sawa. So the other one was for Q plotting, and hata Q plotting utapata the same. Let's see, yeah, this is a Q plot. In unaona the shape here, we consider this part here, na ukiteremka hivi, hii sijui ni kwa nini na misbehave hapa, I don't know why, but it is also in.
Can you also use QQ plots to conclude the same?
QQ plot. Yeah. Actually, you can also use QQ plot. Yeah, you can also use the QQ plot. You can check on the ACFs, the ACF and PACF. Let's see. Check. This is the ACF. Let me check on the other one. And the ACF. And the ACF. Okay. I want you to be very keen here. And ICF, we have the starting point of 0. I want you to tell me the difference. But under PACF, we always don't start at 0. Why? ACF, why do we start from 0 and ICF? Why do we start from 0? Okay, I can start this as a question. Nikiwaambia nitawaambia kila kitu. Why does ACF start from 0? Why does ACF of time series data start from 0? So hii utaipata pahali kwa project yenu, na kwa nini hii inaanza from not from 0? So yeah, now remember, this is our model. From that point now we can forecast. Forecast our model. So and let's see our original plot. So we have the plot K. So this is our original model, but I'm sure you cannot autoplot the model itself. Let's see. The model will give us the unit circles also, but now sitaki hiyo. I only want the model. So now from my model I can forecast using either different confidence level you can specify, and the syntax for forecasting is very simple. You first of all insert your model, then you specify the level of confidence. From there you specify the point ahead, the point that you want to forecast or to predict. For example, my forecast is equals to, I want to forecast model with 95% confidence, and I want to have an output of 20 more points of forecast. When I call that model, when I execute that point and I call my forecast, and let's see, let's see. Remember our values was ending at let's see, K. Check my model here. This was our data. So if I want to forecast, I expect to get the data from 2022 December onwards. So let's have those points. So I expect to have data from 2022 December. Let's see. Check my forecast from December 2022. I expect to have this point. This is the logarithm of 95, and these are the other point, the HIs of 95. So my interest was on the forecast endpoint, and from this point you can either round off from 707. Here we have 708, so you can have your forecast endpoint, and you can plot them. Let's see how you can plot. So I can plot my forecast. When I plot my forecast, I have my forecast here. This is the forecast of my model. I have a forecast from ARIMA of under 100 with non-zero mean. So this is the part. This is the part. So we have we can now run the summary of the model. Let's see the summary of the model. This is the summary of the model. Now, what is ME? What is ME? What is ME? What is the use of mean? This is the mean absolute. What is ME? Guys, what is ME? What is ME? ME
Many of the errors.
is the mean of the error, the margin of error, or rather the margin of error in statistics. And this is actually the degree of error in result received from our point. In result received from our point. And how do we interpret RMSE? This is the root. The root mean square errors. This is the root mean square errors. What is root mean square errors? This is used to measure the difference between values predicted by a model or an estimator Yeah. What is my MAE? What is MAE? This mean absolute. This is the mean absolute error, and this is actually the error between paired observations. Between this is the error between the paired observations, expressing the same phenomena for our case, the point, and the predicted ones, sindio, and the predicted ones. Now what is we call it mape. What is mape? Mean absolute percentage error. This is the mean absolute percentage error. This is a metric that is defined, that defines the accuracy of forecast. It defines the accuracy of our forecast. So our accuracy of forecast is at, you ignore this negative here, it is 4, it is 4.8% from the actual point, from the actual point. That is not map the mean absolute percentage, the 18%. It is our model is 18% accurate. Yeah. What is masse? Now this is how you interpret output from this analysis. This is the mean of the accuracy of forecast. This is the mean of accuracy of forecast. So it's a measure for determining the effectiveness of forecast. So if we use our forecast, if we use the predicted point, we will get 61.7%. We will be 61.7% accurate. so accurate. Yeah. What is ACF1? What is ACF1? What is ACF1? This is autocorrelation of errors. This is just the autocorrelation of the error. This is the autocorrelation of the error. That's how we use what? That's how we use those theories to do prediction. Nani amekamata kitu before we go on what we are supposed to cover today? Mr. Malvin? Rama?
Yes, I'm following through.
I think you have understood one or two, Cindy.
Yeah.
Okay, Mr. David. Mr. David?
Yes, sir.
Have you understood the syntax for TS function under time series?
Yes, I have to do a lot of revision. No.
Yeah, you have to do a lot of revision.
Mm.
And the others, so that you can sharpen yourself well. Let's continue with something else now. So the other part on what we were supposed to cover today was on the basic statistical test using R, and hatutamaliza. I would just introduce some of them with the examples, then at your own time you will go and do more revision on the same. Sawa sawa. Clear waitimo. By the way, some of you should be serious, eh? See, you just join class and you leave your phone there. Out and benefit from the class. So we can continue now. R can carry out a wide range of statistical analysis. So some of these simple ones includes, we have summary statistics like mean, standard deviations, and we have another one called two sample difference test, t-test. We have non-parametric test, u-test. We have matched pair test, that is Wilcoxon's. We have associations test, that's the chi-square test. We have there are many. We have the maneuver, we have the analysis of variance. There are many. So but I just included some. And what is the difference between parametric and non-parametric tests? What is the difference between parametric and non-parametric tests? Any one of you with an idea? Mr. Morris? What is the difference between parametric and non-parametric tests? Or what is the difference between parametric and non-parametric? Hey, no idea. Parametric tests, parametrics, we do tests on outcomes that follow a specific distribution model. So that is when we do tests that are parametric. And non-parametric test is these are tests that are done to conclude or to conclude on observations that does not follow a specific distribution model. And R has a range of functions for carrying out the summary statistics, so I just picked some, and we have some. I'm sure you have dealt with some here. Yeah, we have come across those ones early enough. We have sum of x will just give you sum of that particular variable called x. We have mean, will give you just the mean, median of x. Largest number, we use the maximum. Smallest is minimum. Standard deviation is d of x. Variance var x. Number of length, we are using the length center. We are using length to return those points. For example, these are just simple things, so just going through them as happen. We have x, we have sum of x. For example, you can have that sum of x. Mean of x, you can have it. Median, you can return the minimum. Standard deviation, variance of x, length, quantile of x, yeah, you can have those things there. And if your data contains no element, what will happen? The not applicable element, we set the none.rm is equals to true, so that the compiler may return only the specific values. So the result may show as null. May show as null. So you can overcome this in many ways, but not at all. Commanding by adding na.rm is equals to true. Okay, in a layman's language, what does na.rm function does? I want to hear from you.
Excuse me.
Yes.
On those functions that you have executed.
Yes.
When, for instance, you execute the minimum of x.
Yes.
It's giving 1.
Let's see. Minimum of x, it's giving me 2, not 1. This are vector, sindio? Si mnakumbuka venye tulisema about this.
When I do it on my part, I am getting 1, but maybe just not clear why it is giving me. Okay, sorry. I think we got to keep running x and then the function.
Yeah.
You have to execute.
You have to execute this one
the
first.
data.
Yes.
The data and then okay. All right. Thank you.
Yeah. So you have to execute this one first, the data first, before you execute these other commands. Sawa. Okay. Now, what is the use of na.rn? When we set na.rn is equals to true, what do we mean? Hakuna idea, guy. na.rm in R is actually used to exclude what? To exclude missing values when calculating descriptive statistic here. So what I'm doing here, for example, when I execute this point here and call the mean of x, I'm getting null. So my compiler has included the not applicable point together with the other point. So then mean of x, then you use comma, na.rm is equals to true. I'm telling the compiler to exclude what? To exclude the na values. And when you run this command, you will get the mean. But if you set this to false, what will happen? When you set that to false, what will happen? You get na, you'll definitely get na. So here you are telling the compiler, do not exclude. So just include all points that are forming vector code x. So that is the use of true. That is the use of true. And we have
so in that case, does it include for the division part or the denominator part, does it include the count of the values NA, or they are not counted?
They are not included.
Okay.
Yeah, they are not included. So you can just do this. Just copy this X here and have it here. Let's see, and just remove this now and this one here. So then run the command. From there, return mean of X. So there. So now we are getting the same answer. So now.rm, it will direct or trigger the compiler not to include the not applicable point. So yeah. From there we can do a t-test. From there we can do a t-test. Student t-test is just a classical method for comparing mean values of two samples that are normally distributed. That is, they have a Gaussian distribution. So such samples are described as being parametric, and t-test is a parametric test, and t-test is that a parametric test. So in R, the t.test command will carry out will carry out this operation of a t-test in several versions of the t-test. So on, because we have many of them. So the null hypothesis and the t-test is that the difference in group means is 0. The difference in group mean is 0. Or rather, H0 M1 is equal to M2. Sindio? All of them, the mean from group 1 and mean from group 2 should be equal, so that the difference is 0. So the alternative hypothesis is that the difference in groups in group mean is different from 0. You remember the right-tailed t-test, or the left? Those ones comes from the claim that from the framings of different questions. So, for example, I tell you student A has more marks, has more mean than student B. So I will have one tail. And remember, the tail can be either from left or right. But if you have not, the question has not specified, you just use the two-tail t-test. And remember, the two-tail t-test, even the alpha will change. Even the alpha is divided by 2. Yeah, kwa wenye wanafanya theoretically kwa mkono. So if what do we do? Do we when we get the p-value, or rather we use the p-value to either reject null hypothesis or fail to reject null hypothesis. Remember, we don't accept in statistics. We don't accept because you are estimating. You are just estimating. You are not 100% sure, but you are just 95%. So that margin of 5 that margin of 5 from 95 to 100 limits us from accepting null hypothesis. So we either fail to reject or reject. We don't accept claims in statistics. So if the p-value is less than or equal to the specified significance level alpha, the null hypothesis is rejected. If the p-value is less than, we reject. Otherwise, null hypothesis is not rejected. So in other words, if p is less than alpha, reject null hypothesis. Otherwise, if p is greater than alpha, do not reject null hypothesis. The syntax for t-test is very simple. You have to specify the value of you have first of all to call the test. The test is t.test function. That's the function that performs this particular function, this particular test. And we have x, y, we have alternative. If we have mu, and variances. So for this part here, these are the different versions that we are talking about. Yeah, so you can have just value of x and y and get the t statistics. You can include the alternative, you can include the point, the mean point, you can include the pairs or variances, either equal or not equal. So from this point here, what is t? What is t? A t-test, in t-test, the value of x is just a numeric sample, and the value of y is a second numeric sample. If this is missing, if this part of missing, the part of y is missing, the command carries out a one sample test. So for the alternative, you want to compare means, so the default is two-sided. That's the default. So you can also specify less or greater than. You can specify less or greater than. The mu, this is the true value of mean. Is the true value of mean. Remember, if you want to carry out one sample test, you can specify the true mean either to be equal to the mean of that vector or that particular data. We have the paired, the default is paired false. This assumes independent sample. So the alternative paired true is used for match pair test. Equal variances. So the default is variance is false by default. Even if you don't specify, by default the variance is false. This treats the variance of the two samples separately. So if you set variance to be true, you conduct a classic t-test using pooled variances. So there are additional parameters that was not included here for because of time, so you have to do or to learn about them. Let's have an example here. When we have values of x and y, let's execute them. That is x, that is y. Then we can test x and y. Yes, we can test t-test of x and y. What I'm comparing, or what I want from this test, I want to compare if the mean in x and the mean of y are equal. And remember, you may get they are equal, for example, but not exactly equal, because we are just estimating. Remember, the confidence level by default is 95. So just learn how to change that confidence interval from 95 to 90, just to vary the significance, the confidence interval. So okay, what we have here is 0.03. Is 0.03. What do we conclude? What do we conclude? What will we conclude, guys? What will we conclude? What will we conclude? The p-value here is less than alpha. The p-value here is less than alpha. How will we conclude this claim? And remember, we have if p-value is less than alpha, reject null hypothesis, and our p-value is less than alpha. So we just reject this null hypothesis. So we reject null hypothesis and conclude indeed the true difference in mean is not equal to 0. Is not equal to 0. So remember, these are our claims. These are our claims. So we reject this and say that the difference in groups is different from 0. Is different from 0. But now, if you specify a single variable, you can carry out one sample t-test by specifying the mean to compare against with. By specifying the mean to compare against with. For example, I may say that the mean of y, I want to compare mean of y and mean of 5 and mean of 5. And let's see. Okay, we can see mean of y is 5.5. And I want to perform a t-test of y. I want to perform a t-test of y comparing the mean of this mean together with the mean of 5. Let's see. Okay, you can see what we have is 0.58. 0.58. And what does our point say? If p is greater than alpha, do not reject the null hypothesis. So for our case here, do we reject or fail to reject? Do we reject or fail to reject? Are we together? Are we together, guys?
Yes.
Aki mumetulia sana. What is wrong? What's wrong with you? Mohammed, Fatima.
Fail to reject the null hypothesis.
We fail to reject the null hypothesis. Yeah, so we fail to reject the null hypothesis and conclude.
I have a question.
Yes.
Okay, in case you fail to reject the null hypothesis, what's the other alternative term? Like there is always another word to be used. Like, is it an outlier or not an outlier?
Outlier what? Okay, it's
because
like
whenever you fail to reject, it means
we
is
conclude.
it an outlier or not an like a conclusion?
Yeah, how do we conclude?
Yeah.
Okay. Rama, can you conclude? I request you conclude for us this one here. I request you conclude for
I
us.
think the conclusion is we fail to reject.
That is
We fail to or we accept the null hypothesis.
no. We don't accept. Never use the word accept in statistics. Remember, we are just estimating. Sindio, we are not estimating at 100%. We are at 95%. So we don't accept. So we just conclude. But what do we conclude for our case?
Okay.
Our p is 0.5. Sindio, so our p is greater than alpha. Sindio, and when p is greater than alpha, what do? We fail to reject. So we fail to reject the null hypothesis. But what is our null hypothesis? We were comparing mean of these two means here. We were trying to compare the mean of 5.36 together with the mean of 5. Now, if we fail to reject the null hypothesis, remember this is an alternative hypothesis. True mean is not equal to 5. True mean is not equal to 5. So the null hypothesis will be true mean is equal to 5. That's the opposite of alternative. Or rather, the alternative hypothesis is the opposite of null hypothesis, and vice versa. So the remark is fail to reject the null hypothesis and conclude that the true mean is equal to 5. The true mean is equal to 5. But if you check here realistically, this is 5, and this is 5.3, 5.36. So at 95% confidence interval, statistically we can say that these means are almost the same. We have that confidence from our claim, that the mean is indeed equal to 5. Sawa. Are we together? Mr. Malvin.
So my question was
Yes.
or was between the two, the null hypothesis and the mean, which one is outlier?
Outlier.
Yeah.
What do you mean by outlier?
Because I think we did this in statistics, and I can remember when one you fail to reject one, there must be a value that will be an outlier.
So we have failed to reject the null hypothesis.
Yeah, so between the mean and the null hypothesis, there should be a value which is an outlier.
So which one is an outlier for our case? What is an outlier for first case? Let me check. Okay, I have understood your question. In statistics, an outlier is a data point that differs significantly from the observation. Sawa. That differs significantly from the outlier. So our point, or rather our alternative hypothesis is an outlier. Are we together?
Exactly, that's what I mean.
Yeah. So the alternative hypothesis is our outlier. So we conclude with the alternative hypothesis. So when you conclude with one, the other one becomes an outlier. Sawa. Sawa, Madeleine.
Yes.
Okay, I think now we can continue, but at least now you can perform a t-test using computers, ndio?
Yeah, hiyo ina work.
Yeah, inawaki sawa sawa. Let's see the other point here. So these simple questions nitaframe questions zenye zinakufanya uchange this confidence levels, these ones here, sawa sawa. We can check on U-test. We can check on U-test. What is a U-test? What is a U-test? Now we have moved from parametric to non-parametrics. Those who did a test of hypothesis as unit, and the U-test is used for comparing the median values of two samples. It's used to compare. These are just the main aim of this command is just to teach you the syntax that you will apply to perform this test. So the U-test is used for comparing the median values of two samples. You use it when data are not normally distributed. So when your data is not normally distributed, what do you conclude? You conclude that it is described as non-parametrics because it's not following a specific distribution model. So the U-test is often called the Mann-Whitney U-test, but is generally attributed to Wilcoxon. That is a Wilcoxon rank sum test. Yeah, I'm sure nikitaja hizi mavitu kama ulifanya unit unaona venye ulikuwa unaziandika ilikuwa kama mchezo tu. So here in R, the command is just wilcoxon.test. Then you specify the data that you want to carry your claim on. So the Mann-Whitney U-test, in Mann-Whitney U-test, the null hypothesis is that the probability distribution of a randomly drawn observation from one group is the same as the probability distribution of randomly drawn observation from the other group against an alternative that these distributions are not equal. These distributions indeed are not equal. So the syntax is Wilcoxon.test x, y, then alternative, the mean, then parent, blah blah blah. So what is x? X is just a numeric sample, and the second one, that is y, is a second numeric sample. If this is missing, then the command carries out a one sample test. So the alternative in our syntax is how to compare means. So the default is two-sided. The default is two-sided unless you specify either one tail, that is less or greater. That is less or greater. And I'm sure you remember the framing of questions by these professors. Atakwambia something is less than, then you use two-sided, then you will get wrong answers. So you can also specify either less than or greater. The MU is the true value of median that you want to include in your test, or the median difference. So the default is always 0. The default is always 0. Parent, the default is parent. The default is parent is equals to false. So this assumes independent sample. So the alternative pair inakuwa ni true is used for matched pair test. Let's perform this test here. We have a red bulb and orange bulb. We have these two here. Let's execute the red bulb and orange bulb. Then you can specify, or you can carry out the Wilcoxon test, just a normal Wilcoxon test with the two vectors of red bulb and orange bulb. Yes, we have the output here. This is a Wilcoxon rank sum test with continuity correlation. So data red bulb and orange bulb. This is the Wilcoxon test here. This is the Wilcoxon test, or the test statistic under this test is 19.5. So if you are using mathematical tables, are they called mathematical table or statistical tables? You will compare this point with the point of Wilcoxon in your table. So but because I'm using computer, I just use the p-value. So the computer will just give me the p-value, and the p-value is 0.207. What happens when the p-value is greater than alpha? We just what do we do when p-value is greater than alpha? Do we reject the null hypothesis or fail to reject?
Fail to reject.
We fail to reject. So we fail to reject the null hypothesis. Remember, the alternative hypothesis under this test is true locations shift is not equal to 0, and the null hypothesis is true location shift is equal to 0. So what is our conclusion? What is our conclusion? How do we conclude? Rama? What is the remark first? Fail to reject or reject? Okay, let's continue. Let's do paired test, and the paired sample t-test is just used to compare the means between two related groups of samples. So in this case, you have two values, that is pair of values for the same sample. So to perform paired sample t-test, comparing the means of two paired samples x and y, the R function t-test can be used as follows. We have t-test x and y, then we pair those x and y, and the alternative, it can either be two-sided. So x and y are numeric vectors. Paired is just a logical value specifying that you want to compute a paired t-test. The alternative hypothesis okay, let me check. vitu niliandika hapa hazimake sense. The alternative hypothesis allowed value is one of two-sided, and by default is two-sided by default, greater or equal or less if we want one-sided test. Here we use an example. We use an example of dataset which contains the weight of 10 mice before and after treatment. Before and after treatment. We assume that the mice are sick. We record their weight and record their weight after they receive treatment. Let's check on the same. So we have values of before here. These are values from before. We have for after. Let's see. These are values for after. Then from there we can create a data frame. We can create a data frame. Let's see. You remember the syntax for creating data frame? We use the function data.frame. Then we have group and the weight. From there I can call my data. So in my data I have under my data I have the group and weight. I have one column for group and the other column for weight, and from that point now we can execute the parent. T-test. But now we have to check whether our data is normally distributed. So these are conditions for this particular test. The one condition, your data should be normally distributed. Another, your data should be they should be random. It should be independent. Yeah, those things. But now for my case I have included the normality test for this particular data. I want to see, are these data normally distributed? And one test that is used frequently, even in SPSS, in other softwares, is the Shapiro-Wilk normality test. So I used this test to check if those particular data are normally distributed. We have the test. Remember, in every test you must have the null and alternative hypothesis. And the null hypothesis is the data are normally distributed. Under the alternative hypothesis, the data are not normally distributed. If you have the alternative and null hypothesis, what else do you need? You need only the p-value to tell if your data is either normally distributed or not normally distributed. And D check, I want to compare, I want to compute the differences. I want to compute the differences in groups before and after. In groups before and after. So what I'm doing here, I'm subtracting the first part here with the other one after treatment. Let's see. For example, this is 192.8. So we are getting those 192.8 from 200.1 minus 392.9. And get this part here. The second one is 190.9 minus 393.2. We get 202.3. So from that point I want to check, is this data normally distributed? Shapiro-Wilk tests. Syntax is Shapiro.test. Then you specify your data, then you just specify your data. Let's see. Okay, after executing your point, or rather your command, you have the Wilk test statistic here, that is 0.94536, and you have the p-value of 0.6141. So you use this p-value to reject or fail to reject your null hypothesis. So from this output now, the p-value is greater than the significance level of 0.05, implying that the distribution of difference D is not significantly different from normal distribution. In other words, we can assume the normality. We can assume the normality from this part here. So we can assume the normality. From there we can compute this test using two methods. We can do those tests using two methods. And the first method, we can use the data from before and after direct, or we use the data frame name. We use the data frame that we have just created. Compute paired t-test method 1, where we saved our data in two different numeric vectors of before and after. Let's see. We have a vector called before. That is the data before, and we have another one that we call after. Yes, we have those two. From there we can compute the t-test, where we have the syntax is t-test. You specify the two entries or the 2 vectors that you want to perform this test on, that is before vector and after vector. Then paired is equals to true. Yeah, we are telling the compiler that we are doing paired test of these 2 entries. So when we execute this point there, I have assigned them res, then I compute this res here. I have there, we have the output, we have the output, we have the output. So we can check the second method. We can check, we can have a look on the second method. And the second method here, we specify our data. Remember, you can use function inside another function in this language. For example, I've used data equals. This is a function in R that is used to store, or to not to store, to return the data storage. So data is equals to my data, and weight, in weight, then I look on groups, so let's see. So I check on groups and I return my point there, so I'm getting the same. So how do we interpret this part? The p of the test, this part here, this is the p value, this is the p value. This number is very, very small, 6.2 times raised negative 9, raised to negative 9. So this number is less than the significance level alpha of 0.05. So of 0.05. So we can now reject the null hypothesis. Remember, we reject when the p-value is less than alpha. So for our case, we reject the null hypothesis and conclude that the average weight of the mice before treatment is significantly different from the average weight after treatment, with p value of 6.21, with a p value of 6.21. Sawa. Yes. Do you have any question up to that point before we continue? So from that we do a chi-square. From chi-square, yes, nitaonyesha kitu ingine yenye tutafanya manually. Chi-square test. So chi-square test. So this is test for associations. So test for associations are easily carried out using the chi-square dot test command. So your data need to be arranged as a contingency table. Your data need to be arranged as a contingency table. Here is an example, and before we continue, the null hypothesis under the chi-square is that it assumes there is no association between the 2 variables. There is no association between the 2 variables. The alternative, assume there is association between the two variables. Remember, alternative hypothesis is framed based on your question. So, but generally we assume that there is no association between the two variables. But if your professor frames a question and tells you that the association, or rather he thinks that association in part A is greater, no, I think it is just like this one. So it will assume that there is no association between the two variables. So we call a function called the mass. So let's call it. So I expect one of you to ask me, what is the use of this package? What is the use of this package? What is the use of mass package? So this package includes a lot of useful functions and data examples, including functions for estimating linear models through generalized least squares, or the GLS. So when we call the str of cas93, we have this output here. And from this part now, we can just have a view on this. Let's have a view on this part before we continue. We have cas93. We have cas93. We have cas93, and so this code here shows data sets that has many factor variables which can be considered as categorical variables. And for our model, we will consider the variable called Hamburger, and type. We have two variables inside here called the Hamburger and type. So here we aim to find out any significant correlation between the type of car sold and the type of Hamburg in it, So if correlation is observed, we can estimate which type of cars can sell better with what type of Hamburg. With what type of Hamburg. So we can just load these packages from this part. Let's see. We can load these packages. Then we can call the output here. So we have cars.data. We have created a data frame. We have created a vector called car.data using the data frame function. Cars 93. Then we choose Hamburgs. We have cars 93. Then we choose the type. Are we together? And we have car.data, which is equals to, we are just tabling this part here. Let's perform the output here. Let's see. You can just call the car.data direct before you proceed. Car.data. So this is the data that we are getting. Car 93 Hamburg. We have car number 1 has no Hamburg. It is of type. It is a small car. We have number 2, an Hamburg, that is driver and a passenger. Then we have this is a mid-sized car. Number 3, we have drivers only. That is a compact type, that is a compact type. Number 4, we have driver and passenger, which is a mid-size, which is a mid-size car. Sawa sawa. And we have another driver only, which is mid-size. We have another driver, which is lunch. We have the mid-size. We have the lunch. We have none. Sawa sawa. We have none. Now what we want to do here is just to create a table of all these data sets, then print the outcome, which will be a contingency table before we execute the chi-squares. Let's see. From there you can call the chi-square printing the car.data. So from this part we have drivers, the driver and passengers, cars that are compact. We have 2. Driver and passenger cars that are large, we have 4. We have mid-size 7. We have small 0. We have spot 3. We have 1 0. Sawa sawa. This is just a contingency table that is used in that you can use to carry out this test. So in the same contingency table that you use to add the rows on this side and add columns on this side, and you can have the whole output, or rather the sums that must be equal here. We can perform the chi-square test now. We can perform the chi-square test, and we want to print chi-square.test of cars.data. Remember, this is our car.data. This is our car.data. Let's see. Okay, you can see what we have here is the Pearson's chi-square test, and x squared is that 3.001. so this is the value that you compare with the statistical, with the t-statistic that is present in your statistical tables. We have the degrees of freedom, that is 10, and we have the p-value, that is 0.002723. How do we conclude on this part? Using this p-value, remember this p-value is less than the significance level of 0.05 of 0.05. So the result shows that the p-value is less than 0.05, which indicates indeed there is a strong correlation. There is a strong correlation. Let's have example 2. Let's have example 2. And example 2, we have data table, which is a matrix of which is a 3 by 2 matrix. Let's have it output here, and on data table we have it here. So this is the data table. This is row 1, row 2, row 3. This is column 1, column 2. Remember the syntax for reading matrix data? You remember? For example, how can you return a value in row 1, column 1? Just a reminder, it was not supposed to be in our topic here. Data table, then we used a closed bracket. You can specify 1, I'm sure I'm just have, you can specify either row 1, column 1, you have 35 with you, so all these things. But now let's be back on what we are doing. Chi-square.test data table and correct is equal to false. What is the use of this correct is equal to false? What is the use of correct being equal to false? So the correct false option in chi-square test is a function that turns off its correlation for the chi-square test, which is used with small sample sizes. So guys, and it will give us the standard chi-square test statistics. So the option is mostly used in contingency tables. So students, you can research on how to carry out ANOVA, that is analysis of variance, together with the MANOVA, using R. Using R. Using R. That is it. Nani ako na swali hapa before we do on the markdowns and the lesson? Any question? Any question? Malvin? Mr. John? Mr. Malvin John?
Yes.
Watu wanafloti ama nini?
Me, I'm not floating.
Watu wametulia sana bwana.
I'm just okay. Maybe they are wordless.
Okay.
Maybe the need in a digest pole.
Pole.
The content is being digested.
But si unaona hizi ni vitu zenye watu wanasoma tu campus, si ndio?
Yeah, ziko tu uni most of them. Ida hiyo Python and from the start ya hii kitu hizo hatujaona.
Gani?
Like Python and from the start when we started this R. Hizo zikuwa familiar. They were not familiar, but right now I think
unaona kitu.
Umewaizipitia kampo.
Okay. Umewaizipitia, si ndio? So what we were doing, tulikuwa tunafanya programming, si ndio? So lazima kwanza ufanye programming, then from there unaenda to use that programming now to analyze what you want, si ndio? Yeah, so si umeona mzee anaweza kuwa na project on time series analysis na atumia R vizuri tu na atoboe ukitumia examples ya kwanza nimepeana, si ndio?
Yeah.
So I think it's good. From there tutafanya the markdowns and from markdowns mambo itakuwa sawa, si ndio? Sawa. Now we have something that we call markdown. Imagine you can write all your project from the start up to the end ukitumia hii kitu, ukitumia the R Studio. Sawa. And from that point you can just produce that R Markdown. Either you can produce your document either in Word or in PDF or in PDF format. Sawa. And I want us to do a simple R Markdown. A simple R Markdown. Let's see. You just click on files. So. Then you click on new. Then unaenda chini kwa R Markdown. So. You go on R Markdown. Let's wait. Let's wait. This is called R Markdown. Okay, we can now continue. So we want an R Markdown. For example, here you can specify your name. For example, my name is Bernard. This is title. Title is time series, for example. And the other, you can say this is Bernard. Yes, that's indeed HTML. Ika kwa HTML, I can say okay. Let's wait. Yes, you can see we have time series. That's the title. We have other. We have 2023. This is the date. Output, this is just an HTML document. And when you need this document, what is inside this? Do you see here? This is R setup include first. So anything that you write inside this R part here will be a command, will be an R command, but on other parts they are just ones. They are just ones. These are pressure, echo, force, blah blah blah, all those things. So when you need this document, just click on it here, knitting a document. Okay, let me see. You can use this canini here, this arrow next to knit. Then we have knit to HTML, knit to PDF, knit to Word. For example, I want to knit to Word. I can click OK and give my word. This is R Markdown practice. R Markdown practice 1. So you can click on save. Let's wait and see our Markdown. Let's wait and see our R Markdown. Itakuja tu, just be patient. I think you can see what is happening. Yes, the title of document is Time Series by Bernard Moredi. By Bernard, you can see that this is an R Markdown. Then we have blah 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 blah, all these things here. So these are just simple things. And now I want us to do something else. Instead of having these ones here, I want us to do want us we need this one here, tuone itafika wapi. I'm sure you are doing the same from your side. Let's wait. Good, yeah. That one will come out clearly, and I want us we have our point. Let's see. And now inside here we have inside here we include this part, the part from the one. So everything there is inside that point. So we can need it one. Let's see. Output create, and let's see what we will get. Okay, let's see. So this is our data. This is our plots here. Imekuja tu vizuri. These are our plots. You can see this is how we convert this, or rather this is how we produce an R Markdown. This is how we produce R Markdown. So you produce your reporting directly from R to Word. So or you can knit it directly from R to the PDF. Wah, nimechoka. Okay, we can call it a day. Nani ako na swali before we end? Or nani ako na anything ya kusema? Sababu
okay, I have something to sound.
Yes, sababu hamutaniona tena.
So it's like it's the end of the program, or the end of this package.
The end of the program.
Like, are we done with the program?
Yes, we are done with the program.
Then, by the way, there is a question again. Why didn't you offer C+?
Okay, we were dealing with we were more concerned with the data. So the field of data science.
Yeah.
And in data science or statistical computing, C++ is just a language to train you so that you can be able to program well using either Python, R. So that's why you will that's why you will see in most campuses. For example, for my case, I did C and C++ at the same time. So C inatumika kwa statistical computing sana.
Like, is there any difference between the C plus and Python because like in VS Code you can do a C plus there.
Okay, hapa sasa ukweli sitakwambia sababu I don't know Python. Python
Mm.
sijui, nilisikia tu mnasema anaconda, sijui nini. Ukweli sijui Python. Yeah.
Okay.
Mm. So
Okay, like any application where we can use this R.
yeah.
What project, what design, what can we make like from Python? We are told that you can, if you are good in Python, you can create an app,
Yes,
you can
yeah.
create many things.
Yeah.
Like so in R, what can you come up with?
R, I remember very well. There was a day I sent. By the way, what do you think is the difference between the two languages? What is the difference?
I think Python is more of everything, can do anything, but R is mainly restricted or confined on statistics, finance, things dealing with numeric numbers or math. But Python can program most of
Yeah,
the
yes.
things.
Actually, that's okay. Even in Google, Python is a general purpose programming language. Sawa sawa. So you can use Python anywhere. So as data you can use it as data analyst, for example, as web developer. But interface yake na ya R ni gani unaona ikiwa friendly kwa data analysis, Mr. John? But now R is just
Kindly pardon.
uh, kwa Python na R ni gani unaona ikiwa more friendly in field of data analysis?
Hey, the Python.
The Python.
Yeah.
Which course are you taking?
Me, I'm taking computer science, like the software
Yes,
engineering.
yes. That's why you have to go with the Python more than R, because R, eh?
Mm.
Because R is a
Yeah.
statistical programming language.
That's why I'm not common with it.
Sawa sawa. I'm sure umekutana na
Yeah.
Python somewhere, even before you introduce
Yeah.
kwa yenyewe. So that's your area. But as a statistician, I advise you take this language seriously more than Python. But I'm not demoralizing you. Sawa sawa. Okay. Aki, sinisikia sauti za watu tu nikiondoka sababu hatutaonana tena. Where is David? David.
Yes, sir.
David, hii.
For me, I would say thank you for being a very, very, very resilient trainer that has come out very strong.
Thank you so much.
Uh, I wish I could have. I think on the first round for students, things, they were not wrapping up. But so it's taken a lot of time has been lost in terms of us trying to understand where is this fitting in.
Yeah.
But then as we went on, things have started. Like now, the today's class, for instance, even as you went from one package or one library to the other,
Yes.
we could clearly identify that this is for this purpose.
Yeah.
So I don't know whether we can have another opportunity to go at it now with the with the background of we needed data science and then now we reapply it again because we can see they are very rich areas, and I now can see where I had a gap
Yes.
in terms of previous usage. But you've really tried to bring home the whole thing. It was very expansive, uh, but you remained very, very, very consistent. And I hope you'll have more opportunities to interact with more students. I think you can really impact very well.
Hey, thank you so much.
It was a
More,
long journey. I mean, it was 3 weeks you did
yeah,
every evening.
yes.
Yeah.
Together with the Python, together with the SQL,
Yes,
four
yes, yes.
weeks.
4 weeks.
Yes.
That was a long journey, and you were very persistent and very consistent every evening.
Oh, thank you so much. Ni hii wiki tu stima imekuwa na maneno, but we have done. Sindio? We
Yeah,
are done.
yeah.
Okay, Fatima, a review from you.
Hi.
Hi to
I don't have much to say, but I'm grateful and I appreciate the time and effort that you have put into this. But I've
okay.
learned a lot. And I'm just happy that now I know something.
Oh, thank you. King Mula mwenyewe. King Mula. I think if